Hello, everyone, and welcome to today's LinkedIn Live. My name is Sarah Barnes-Humphrey. I'm the founder and host of Let's Talk Supply Chain. And I am so excited to be collaborating once again with the team at Manhattan and Associates. Now, we've recorded 4 episodes together for Let's Talk Supply Chain, and we've talked about supply chain unification, planning, forecasting, and transportation management. And so I am really looking forward to another really fantastic discussion with them today. So a warm welcome to Jeff and Mandar, and I'm so excited for them to join me today. Now, today, we're going to be talking about demand forecasting. Now, our current supply chain landscape is defined by disruption, complexity, volatility, and everyone is trying to juggle that, trying to get a jump on the next disruption. But unfortunately, most of our traditional forecasting methods are no longer fit for purpose. Ongoing innovation is essential, but like so many other areas of supply chain, and in life, it really is a continuous journey, not a destination. There's not really a silver bullet solution right now, but the increasing demand for forecast accuracy is driving some incredible advancements across the industry. The rise in AI technologies like machine learning is driving real competitive advantage for businesses. And for those businesses that embrace the mindset of continuous improvement and evolving innovation, those small improvements are generating big results. But what happens when forecasting fails? Every year, companies across industries lose millions, sometimes even billions, due to inventory misalignment. Overstocked items lead to costly markdowns and waste, while understocked products result in missed sales and disappointed customers. So the big question that we're going to be answering today: could smarter AI-driven forecasting help prevent these losses before they happen? So if you're here in the audience, I want to hear from you. Put it in the comments. I want to know where you're tuning in from, and make sure to get your questions ready. Add those into the comments as well, so we can go get to those a little later on in the show. But before we do that, we need to get to know our guests for today. So welcome to the show, Jeff and Mandar. Jeff, I'm going to start with you. Can you introduce yourself? Tell us who you are and what you do.
Sure. Hello, everybody. My name is Jeff Beadle. I'm Senior Director with Manhattan. Been with Manhattan about 26 years, come up in 27 years this September, all in R&D, and focused on the science that goes into our products. So I lead the group that focuses on all the mathematical optimization, as well as the data science, AI, and ML that goes into our products.
Yeah, and you can catch Jeff because you were on an episode of Let's Talk Supply Chain. So you can catch him over on our website as well, going into a little bit more depth as to what you do on a day-to-day basis, because it's fascinating. And of course, Mandar, welcome to the show. Tell us who you are, what you do, and give us a little bit of insight into Manhattan.
Sure. So Mandar Rahatekar, I'm Senior Director. I'm also with R&D. I've been with Manhattan for the last 4 years. I've been a supply chain practitioner before I joined Manhattan for the last 20 plus years. I lead the product design team. So my team is responsible for designing the features that are seen in the supply chain planning solution. As far as Manhattan is concerned, Manhattan provides supply chain software solutions end to end. So we have supply chain management solutions, which has warehouse management, labor and transportation management. And then we have our Omni suite of solutions, which is on the front of the house, so that has point of sale, store inventory management, and order management. And then last and definitely not the least, which is the focus of today's discussion, is supply chain planning, which includes demand forecasting, allocation, and replenishment.
Yeah, and you've been on the show as well. So I highly recommend you go and check out both of their episodes, because we go into a lot more depth. So let's start with some context and definitions so we're all on the same page. Jeff, I want to start with you. What does traditional forecasting look like versus AI or machine learning? What is the real difference?
Yeah, so traditional forecasting is usually done by statistical time series based models that use linear methods and require explicit design assumptions. Basically, they're kind of a predefined set of equations or formulation that then iterate over the data. And these usually range from general models like exponential smoothing or RIMA and a whole wide variety of variants of that, to more specialized time series models, let's say Holt-Winters or Crostons. Now, machine learning, on the other hand, are for the purpose of demand forecasting, are typically regression models that are built purely from data using complex algorithms and techniques that can autonomously detect, learn, and model nonlinear relationships of the variables and inputs and the target that you're trying to forecast without any of those predefined equations.
Awesome. Awesome. And I think forecasting has become, a lot more difficult. And so we want to talk about how we can take that traditional into the future. And let's dive a little bit deeper into machine learning. Talk to us about how machine learning algorithms detect those patterns, predict anomalies, and help to self-adjust. I mean, is that even a thing? I want to know.
Yes, yeah. I think that one of the things that, obviously, probably a lot of people are aware that machine learning requires a lot of data, and I'll get into that here in a second. But the thing that I think some people don't realize is machine learning, how it really fundamentally works is it's guided by mathematical optimization within the learning process. As it's working through all of the data, trying to model relationships within the data, it uses optimization. That's what provides a lot of the robustness and guarantees, if you will, that when you come out of it, along with some other techniques that you have to validate performance, it can lead to a very solid mathematical modeling representation of that predictive model. Getting back to the data, like I mentioned earlier, it learns directly from data, purely from data, right? So there's no pre-programmed or explicit programming in the learning algorithm. It has to build all that inference and understanding purely from data. And because of that, and the way that the algorithms are designed, they can be very complex, but not in a bad way. They can become as complex as they need to be based on the problem they're trying to solve. And these can use a variety of techniques and model structures like tree-based or graph-based or neural networks that many people hear about within deep learning and so forth. And these more complicated structures, along with the more advanced learning algorithms, can again capture these nuances and relationships amongst the data. Another key point of machine learning that helps it figure out these patterns and builds good predictive models is it has an innate built-in feature selection engineering process mechanism within it. And what that means is a feature, or is like a predictive variable or an input that goes into a model, it assesses and learns kind of its usefulness, if you will. And sometimes it can remove it, it can strengthen it, it can rely on it more, it can adapt it over time. And so it can grow and expand kind of its knowledge of how to more appropriately predict demand. And it has continuous learning. That's the one other thing I wanted to mention. It can continuously learn. As it gets more data, it can refine its understanding and adapt over time.
So I can really see, and that was actually one of the things I was going to ask you, is as we feed it data, as we ask it more questions, can it then do better predictions? And when we talk about self-adjust, I guess it self-adjusts through the data that we're inputting into the system.
That's right. Yeah. Yeah, exactly. To point out, to connect that, to the self-adjusting piece. That's the continuous learning aspect, and this autonomous mechanism internally guided by just optimization that it can go through that process.
Awesome. So as I mentioned in the intro, forecasting innovation has been and continues to be a journey. I feel like we all want it to be a destination, but I think it's going to be that continuous learning, that journey. So can you talk to us through the shift from historical trend-based forecasting to AI-driven predictive intelligence? Like, what were the key factors driving that? Mandar, I'm going to start with you and go with, and then go to Jeff.
Sure, thanks. So to me, it's two things at a high level. One is consumer behavior. I mean, we all as consumers are shopping online more, which automatically means there is more data available. And for any machine learning model to be effective, it's not always true that more is better, but having access to more data can figure out which data points are usable, right? So the starting point is getting more data and then figuring out what is the right data set to impact forecast. So we just have more data available now. I mean, that's just the fact of it. I mean, all of us have seen this happen, which sometimes seems spooky, is you make a search for some topic and suddenly it shows up on all possible screens and searches. I mean, I'll mention a funny thing. Recently, me and my son were just chatting about how different ball players catch across the different across globe. So India, where I grew up, there is a certain way to catch a ball, and then he was telling me how he grew up. What's the technique? And lo and behold, next day I was on YouTube, and suddenly a search shows up about the physics of catching a ball. Mind blowing to me.
That is so creepy.
It is. It is creepy. At the same time, we are all now used to it, especially the next generation. They expect these things to happen, right? So point being, there is more data available. There are so many dots that get connected, and search results are just one example of it. The second one is just the technological capability. I mean, the amount of processing power that we now have compared to even just 4 or 5 years ago or a decade ago is exponentially growing. So a combination of more data and more processing power leads us to the ability of using these more enhanced statistical or machine learning models to provide better forecasts.
And I have a question before we go to Jeff, but because more data doesn't necessarily mean more good data.
Mm-hmm.
Right. So how are we making sure that we're putting in the correct data versus bad data? Or how are we sort of mitigating that?
Mandar, do you want me to?
Yeah, please go ahead.
Okay. Yeah, so that's a great question. And that is kind of more of I would say maybe a recent problem. At first we didn't have enough data. Then all of a sudden, we have all this data. Now we're like, well, hold on, we have a lot of data. How do we properly sift through it and understand what is most relevant and so forth? And I'll touch on that a little bit later, actually, because that's a great point. As we try to leverage more machine learning, especially in the context of external data, we have to be able to continuously assess the applicability and relevancy of data that we're considering.
Well, and I think it has to do also with trusting the data as well, because the people who are using it and are able to use it to predict some of those outcomes in the forecast and things like that, trust is a big issue. And knowing that the data that's going in, and I know we're going to talk about this a little bit later, but I just want to put it out there just in case anybody has any questions, wants to put that in the comments for a little bit later, is that trusting that data is a big key factor of that. So Jeff, I know I took us on a little bit of a different curve. Did you want to add anything to some of the key factors that are driving sort of that trend-based forecasting into the AI-driven predictive intelligence?
No, I was going to talk about computational power and kind of the advancement. So I think Mandar already touched on that, the data availability and really the diversity of data as well. And some of that data availability piece has really been accelerated and matured and hardened through a lot of digital transformation initiatives that companies have been doing, for the past 10 years or so. And many are still on that journey. That's very important. And to really help advance this further, because a lot of, you can have the most powerful machine learning algorithm and model, but if you only can give it limited data, it may not be any better than just, some standard native technique, because it just has limited information to work with.
Because as humans, we have a bit of an innate ability to overthink things. Do you think sometimes that limited data that we're actually putting into the system comes from us kind of overthinking what we're doing with the data and what we're sort of expecting from the outcomes? Because and where I'm coming from with this is kind of as humans, sometimes we have bias with the outcomes and things like that, which we might get into a little bit later. But that's why I'm asking the question.
Yeah, it does. When you have limited data, things become very ambiguous about what to do, about how to make predictions more appropriately, even for techniques that are designed to work with less data, like some of the time series, univariate, type time series models. When you don't have those additional factors in play, you can end up with misguided models. Either typically bias, though, comes through another mechanism than poor performance, like poor accuracy, kind of variability in your predictions. But you can get bias to that mechanism as well.
Interesting.
if you have limited information.
So let's talk about the external data for real-time forecasting, because really this is going to be a key part of this conversation, right? Because we all know that data is one of the biggest challenges when it comes to forecasting. Many businesses struggle with their internal data, like we were talking about before, but then you've also got this component of external data on top of that as well. So Jeff, you and I are going to talk a little bit about this. So let's start with how AI and machine learning helps to harness external data. How can we manage that through AI and machine learning, or how should we be using it?
Right. So machine learning has an innate capability to handle high dimensional data. Basically means that think of high dimensional like a spreadsheet, right? So if I have a tabular data set that I'm bringing into an ML model or a learning algorithm to learn from, high dimensional just basically means I could have hundreds of columns, right? That are input that I'm passing into the model for it to learn against. It's very powerful in that regard. It's designed to kind of handle that and be able to vet that out and weed through that and figure out what is the most meaningful set of features or variables in that data set. External data, how it can come into the ML model is just like that. Think of it as just like another extension or kind of concatenation or appending, an external data set. It could have multiple attributes, right? Typically does. It's not just a single value that you're bringing in with external data. Hopefully not. You want to be able to characterize that data as well so the model can learn from that. But it's just like, kind of bringing in another data set and bringing it together with your existing data that the model has already been learning from. So it's very, very much enabled and can handle that very well.
Absolutely. And so why is having access to this external data so important? Like, why is it really, I think you guys call it a game changer for businesses today.
Yeah.
We're all looking at ways for competitive advantage using not only our technology, but our supply chains as competitive advantage. So how does this feed into that?
Yeah, this brings, excuse me, this brings the demand planning and demand forecasting models closer to reality, right? So if we can bring in more external data, especially more real-time external data, into the model, and so then at inference time when the model is being used for predictions, we get more real-time insights that can be shared into the model that it can use to predict with. So you're bringing that outside in demand planning mechanism and really strengthening that. And you want a modeling system that can be adaptive as well, because the other thing is, like some of your classic things you think from an external data perspective, like weather, or maybe local events, or like some classics. I think of like the automotive industry, like the Polk database, which is a registry by zip code of different cars and their year and make and so forth, and they can use that to figure out how to position inventory to service those kind of cars. Or for pharmaceutical, the flu projections from the CDC and the cough, cold and flu kind of product lines that they have to support. You want a system that can take that in and ingest that and figure out what parts of the overall data, the business data, it's most relevant to, so it can model and use it for that, because it's not going to be broadly applicable. That's part of the challenge with the external data, is you need to have a system that's adaptive enough to where some of that external data may only be very applicable for a small percentage or even 10%, but for that 10%, man, is it impactful.
Well, and I just want to give a shout out to Mackenzie. I see your question. We're going to get to that in just a little bit, because we want to go through some of these questions that I have around data before we get to that. And you're right. Data signals, we talk about weather all the time, especially in transportation, right? Because it can really impact routes.
Oh, yeah.
It can impact, which route we want to take. And it's not just weather. It's also when you think about trucking and you think about a route, the distance between some of the stops, right, that make a difference and can be an external data signal to help drive some of this accuracy that we're talking about. So how do you think that businesses can leverage those real-time insights for demand forecasting? Mandar, I'm going to bring you into the conversation to give us some insights on that.
So bringing in the data, there are many external factors, right? You have the standard indexes that we can bring it in, which is weather. You can talk about this data published by CDC, some of those data sets, but also when I think of external data, if I compare it to the historical data sets that we're looking at, it's for that particular item location that I'm looking at, and how did this particular product sell at particular location historically. But there is also inherent external data within the organization, meaning even if I just look at item locations history for other items. So if I go to buy a particular soda, there may be other soda that influences, depending on whether it's a discount on similar items, that has an impact. To me, machine learning models are better at looking at those, I guess, product affinity impacts, right? I mean, if X sells better, or if the other product is at a discount, what's the impact on the product I'm trying to forecast? There is that external factor. Then if we expand that circle slightly broader to look at